Let's take a look at a few more examples. In example 3, they want us to compute the area between a z-value of negative 0.51 and z equals 0.32. Once again, it's a good idea. Go ahead and draw a sketch of the normal curve. We're still working with z-scores, so it's still a mean of 0, standard deviation of 1. So we draw a rough shape of our bell-shaped curve. We know that the mean is 0, which is right here. A z-score of negative 0.51 would lie somewhere to the left of the mean. A z-score of 0.32 would lie somewhere to the right. And we're looking for the area between the two. So I would shade the part of the normal region between those two z-scores. To find that area, we now need to go to our calculator. Once again, it's going to be the normal CDF command. We go second, distribution. Go down to option 2, normal CDF. For this region, our lower bound is negative 0.51. Our upper bound is 0.32. It's a z-score, that's the standard normal, so it still is 0 for the mean, 1 for the standard deviation. Go ahead and hit enter, and we would get that the area between those two z-scores would be 0.320, and this would round to 5. So 0.3205. Let's take a look at number 4. We want to do to the right of z equals negative 1.75. If you would go ahead and draw your bell-shaped curve, so sketch it out, negative 1.75 itself would be somewhere to the left of the mean, and then we're looking for the area that is to the right of that. We'll go second, distribution, go down to normal CDF. In this case, our left bound would be the negative 1.75. Because it's going to go all the way to the right, that's going to approach positive infinity. So for positive infinity, as a placeholder, we'll use 1, second, comma, to get the E, 99, 0, comma, 1, because it's still a z-score. Paste, and hit enter. And to 4 decimal places, we would get 0.9599. Some extra practice, let's look at 5. Here we're looking for the area between negative 0.5 and positive 1.5. The graph is already done for us. So we can go second, distribution, normal CDF. Our left bound is negative 0.5. Our right bound is positive 1.5. It's standard normal, so it's a mean of 0, standard deviation of 1. Hit enter, and we should get an area of 0.6247. 0.6247. Let's take a look at example 6. Here the region that's shaded is going to be the area to the right of a z-value of 2. To find that area, we go second, vars, to get the distribution menu, normal CDF. The left bound, the shaded region, goes as far to the left as 2. It goes all the way to the right, so our upper bound should be 1, second E, 99. Standard normal, so it's still 0 for the mean, 1 for the standard deviation. Go ahead and hit enter. And to 4 places, this would be 0.0228. 0.0228. Let's take a look at example 7. This is one that you can really do a bunch of different ways. They ask us to find the area to the left of z equals negative 1.28 and also to the right of z equals positive 1.28. If we sketch that out, we have 2 different z-scores now. So here's our normal distribution. It's a z-score, so the mean is going to be 0. Negative 1.28 would be somewhere over here to the left of the mean. And then we're looking for the area to the left of that. So we would shade everything over here. We also want the area to the right of z equals positive 1.28. Positive 1.28 would lie to the right of the mean, and we want the area to the right of that. So we're going to shade everything to the right of that. So we're looking for actually the combined area of two different regions. Okay. There's a few different ways you can go about this. You can calculate the area of each region individually. Here this would be a region with a lower bound of negative 1e99, an upper bound of negative 1.28, 0, 1 with the normal CDF, get this area, get that answer. You could similarly do a normal CDF calculation to get the area in the upper tail. For this region, its lower bound would be a positive 1.28. Its right bound would be 1e99, 0, 1, get that answer. And then just simply go ahead and add the two together, and that would give you the total shaded area. Another approach we could do, if you remember a bell-shaped curve is symmetric. So if you're looking for the area to the left of negative 1.28 and also to the right of positive 1.28, because that's a symmetric interval, all you would really need to do is find the area in either one of these two tails, and it's going to be equal, and just double it. So I could find, for example, the area in this lower tail, like we described earlier, and just multiply it by 2, and that would give us the total area. Or you could conversely do the area in the upper tail, multiply that by 2, and that would give you the shaded region as well. Okay. Alternatively, we could also use a rule of the complement style of idea, because we know that the total area under the curve is equal to 1. If I have that total area of 1, and if I were to subtract or take away the stuff that's between the two z-scores, then what would be left over would be the area in the two tails. So another approach would be to do 1 minus the area between the two, and the area between the two would be normal CDF, left bound negative 1.28, right bound positive 1.28, comma 0, comma 1. Take that away from 1 and you would get negative 2.005. I personally kind of always like to do twice the lower tail area, just what I'm used to. So I'm going to do it like this. I'm going to do second distribution. I'll go down to normal CDF. If I want the area in just this lower tail itself, the lower bound is negative 1e99. The upper bound is negative 1.28. It's still a z-score, so 0 and 1. I go ahead and hit enter, and what I have just found, this number here, represents the area in just the left tail. Again, because the normal distribution is symmetric, the area in the right tail above positive 1.28 should be equal to the area below negative 1.28 for z. So all I have to do is take my answer and multiply it by 2, so times 2. And that's yet another way where you can get that final answer of 0.2005. One of the big concepts, this is one of the fundamental sections in probability theory, is how probability relates to the area. The area under the standard normal curve to the left of a z-score is equivalent to the probability that z is less than that z-score. And the same thing for either right regions or in-between regions. So instead of just phrasing this and wording this as an area question, we can rephrase it as a probability question. For example, let's suppose we choose a z-score at random. What is the probability that our given z-score is less than 0.45? This is something where, again, you could draw a standard normal curve for this. It's a z-score. So you would draw your bell-shaped curve. Z equals to 0 would be smack dab in the middle. 0.045 would be to the right of that. And if they say less than means go to the left. So you would shade everything to the left of 0.45. To find that probability, which we just said a moment ago is equivalent to the area, it would be second distribution, normal CDF. The lower bound, because it's going all the way to the left, that would be like our negative 1e99. It's going to go as far to the right as the 0.45, comma 0, comma 1. Go ahead and hit paste, and we would find that that probability would be equal to 0.6736. 0.6736. Let's take a look at number 9. This is one that we've already did earlier, but instead of calling it a probability, we called it an area. Let's find the probability that z is between negative 2.05 and positive 2.05. Again, it's a good idea. You should be drawing your bell every single time on this. If I draw my bell-shaped curve, it's a z-score, so the middle value would be 0. Negative 2.05 would lie to the left. Positive 2.05 would be to the right. And if we want z to be in between those two numbers, then you'd be shading the area of the region in between those two, which is going to be equivalent to this probability. To compute it, we would go second distribution, normal CDF. The lower bound of the region would be negative 2.05. The upper bound of the region would be 2.05 positive, 0, 1. Go ahead and hit enter, and we would find that that probability to 4 decimal places is 0.9596. So the probability that a z-score is between negative 2.05 and positive 2.05 is about 0.9596. And if we just kind of compare this to things that we've already learned in the class, you might recall from the empirical rule, the probability that z is between negative 2 and positive 2 was 95% or 0.95. Here, this would be just a little bit more to the left and a little bit more to the right. So the total probability, or the total area, should be a little bit more than that 95%, i.e. a little bit more than 0.95. And that's exactly what we have here. We get 0.95 with a little bit more, 0.9596. Let's take a look at the last one. We want the probability that z is less than a negative 1.96 or that z is greater than a positive 1.96. Again, there's really kind of 3 different approaches you could take to solve this one. First thing you'd always want to do is sketch it out. Here's my normal distribution. It's a nice bell-shaped curve. We're still dealing with z-scores in this section, so the mean is going to be 0. Negative 1.96 would be to the left of the mean, and then z should be less than that, so I'm shading everything to the left of that negative 1.96. Or z could be greater than a positive 1.96. Positive 1.96 is right here. I need to shade everything z greater than would be to the right of that, so I'm shading everything over here. It's 2 distinct regions, so you could do it as 2 different calculations. You can compute the area of the left tail using a normal CDF calculation. Compute the area of the right tail using a different normal CDF calculation, and then add the 2 of them together. Also, this is another one of those symmetric regions, so you can simply find the area in either one of the 2 tails and double it because they're going to be symmetric. Or you could use a rule of the complement style approach, which would be to find the area between the 2 of them, noticing that the whole area under the curve is 1. So if you did 1 minus the stuff in between, what would be left would be the area of both tails combined. So either way you want to do it, I'll go ahead and find the area in the lower tail and then I'll just double it. So this would be second distribution. I'll go down to normal CDF. If I want the area in the left tail, then I need to look at the lower bound. It's going all the way to the left. That'd be negative 1 E99. The upper bound for that region that I'm looking at right here is a negative 1.96, comma 0, comma 1. Go ahead, hit paste and hit enter. And that would give me this area right here, which would be the left tail area. Since I want the combined area, I'm just going to double it from symmetry. And I would get to 4 decimal places. It's going to round. It's going to go up to 0.05 because that 9 right here, we'll bump that up to a 10. We'll bump that up to a 10. We'll carry 1 and make that a 5. So 0.0500 would be accurate to 4 decimal places.